So in today's lecture, we will see the fabrication of patterned magnetic storage devices, right? So how the magnetic storage devices will be patterned, right? How the magnetic storage devices will be patterned, and what are the different mechanisms that are being used, how the fabrication techniques have been implemented, right? So this fabrication, we know that the magnetic devices, so magnetic storage devices will be fabricated by different fabrication techniques. Like one of the best techniques where the storage devices can be fabricated is lithography, right? So lithography is one of the technique where we can write certain patterns on any substrate device. So for that, people go for different fabrication techniques. So one of the techniques, as we told, is called the lithography technique, and so regarding the fabrication, that will become under PVD process and CVD process. Right? So in today's lecture, we will see how the fabrication of patterned magnetic storage devices, how the magnetic storage devices will be patterned. Right? So the outline of this talk, offline of this lecture, will be having the introduction regarding the nano patterns and nano structures and different techniques, right? Different techniques. And next one is the available techniques. So that is what we are telling. Available techniques in the sense, what are the different techniques that which we can patternize, that which we can pattern on a silicon substrate, right? How the patterning will be done, what will be the different methods that will be done, and we will compare the different techniques, that available techniques, whatever the available techniques are there, and that will be compared with the next lithographic technique, right? Because we have some E-beam lithography, photolithography, optical lithography, like that we have. So we'll compare. So what is the time of writing, and what is the resolution, and what is the cost comparison, right? So this type of comparisons is what we can see in this type of phenomena, that is what they outline. And there is a description of DIP pen lithography, and we will see some description of the nano imprint lithography, and of course we'll go for summary, and we will and the references where we take certain information where we have taken, right? So introduction, we have the problem. The problem is the super paramagnetic effect limits size of bit domain, and solution is spatially separate bit domain. Aim is to produce patterned memory storage devices, and the current status is production time is around 10 seconds per disk, and other is $1 per gigabyte, right? So there's a production cost. The production cost is $1 per gigabyte. So how much production cost is being done is around $1 per gigabyte, for $1 per gigabyte. So this is what the cost production is, and production time is 10 seconds per disk, right? So the basic aim of this particular device is to produce patterned memory storage device. Patterned memory storage device in the sense, we have a silicon substrate like this, and how the patterning will be done on this particular dimension of the silicon, right? How the patterning will be done. Patterning in the sense, suppose if you want to pattern elliptical pattern, we want to do an elliptical pattern, we want to do a circular pattern, or we want to do a rectangular, square, or rhombohedral, like that. Whatever the patterning we need, so that patterning should be done on a silicon wafer. That is what we call the patterning phenomena, right? So what are the different methods of patterning? As we told, the different methods of patterning are the lithography. Lithography is one of the technique where we can use lithography is one of the techniques where it starts writing on any substrate, right? Starts writing on a technique. So the different forms of lithography techniques are, first one is the interference lithography, extreme ultraviolet lithography, X-ray lithography, E-beam lithography, focus ion beam lithography, and dip pen lithography, and nanosphere lithography. So these are the different types of lithographic techniques. Where the patterning of any structure or magnetic storage devices can be done. So that's what we speak about: interference lithography, extreme ultraviolet lithography, X-ray lithography, E-beam lithography, focus ion beam lithography, and dip pin lithography, and nanosphere lithography. So these are the different methods of patterning. So when we have something like self-assembly, and self-assembly is a block copolymer lithography. This is also one type of lithography. Block copolymer lithography, self-assembly is assembling it. And there is a mask or replica. That is for the nano imprint lithography. We have micro contact printing technique. And direct beam patterning and direct film patterning. and other is the electron beam projection lithography, projection lithography, and focused ion beam projection lithography, projection lithography, and other is a nanoparticle pattern media, that is carbon nanotubes and iron nanoparticles, right? So these are the different types of nanoparticle media, and these are the different types of lithography technique where we can use it, right? And moreover, we have this particular nanoparticle pattern media like iron nanoparticles, iron platinum nanoparticles, and carbon nanotubes also, right? So how they have been, how they will be fabricated, what is the patterning condition, and suppose we need to mask. If we put a mask on any particular, substrate, and based upon the mask structure, also patterning can be done. That is what the nano imprint lithography and micro contact printing technique, right? And what are the characteristics definition? The feature size is what we need to understand, and is the spacing and throughput, and what is the energy. So energy of the beam required, that is what calculated per unit area, energy of the beam required per unit area, throughput, number of features produced per second, and spacing, distance between mesa, and minimum size of the mesa produced, that is what the feature size, that is what the characteristic definition is what we need to understand is. And if you come to the first part, that is the interference lithography, because when we speak about the methods of patterning, first we need to understand what is interference lithography, later we'll go for UV lithography, and we'll go for different types of lithographies, and we'll try to compare the characteristic sizes, and we'll try to compare the advantages, disadvantages. At the same time, we need to see some information behind that. So interference lithography, in case of interference lithography, the characteristic feature is around 75 nanometers. Energy required is 4 joules per centimeter square. Throughput is 10 power 10 features per second. Equipment cost is $10 million. Advantage is a simple procedure. And the simple procedure. Interference lithography is a simple procedure when we do low energy consumption, low energy is required. And disadvantage, in fact, feature size is limited to 75 nanometer. This is one of the disadvantage of this particular interference lithography. Here, we have substrate here. The substrate is being filmed by some photoresistant material, right? And we try to implement some laser beam, and we can pattern it. And this is what the developed fringe pattern in resist, right? And this is RAE edge of resist to fully transfer pattern, right? So this is your substrate, and this is what the patterning that was done. This is what the patterning that was done on the substrate using the interference lithography. We have the characteristics, feature size around 75 nanometers. Energy required is 4 joule per centimeter square. Throughput is 10 power 10 features per second. Equipment cost is $10 million. Advantage is a simple procedure, low energy, and disadvantage is feature size limited to 75 nanometers. So what is the next one is what is the extreme ultraviolet lithography. So when we speak about the ultraviolet lithography, the characteristics of feature size is around 30 nanometer. Energy required is 40 joules per centimeter square. The equipment cost is $50 million, and throughput is around 10 power 11 features per second. And the disadvantage of this particular extreme UV lithography is high equipment cost, energy intensive process, and vacuum conditions required. So these are some of the disadvantages where we can find that extreme lithography has, right, compared to the interference lithography. So if you see the comparison between them, we have this extreme UV lithography. The characteristic feature size around 30 nanometers. Energy required is 40 joules per centimeter square. Equipment cost is $50 million. Throughput is 10 power 11 features per second. And the disadvantage of this technique is high equipment cost, energy intensive process, vacuum conditions are required for this, right? So if you come to the X-ray lithography, the the feature size is around 80 nanometers, and the advantage is high resolution or large area patterning, and basic disadvantage is synchrotron facility required to pattern large areas. Synchrotron facility required to pattern large area, and we have the high power requirement. We have in X-ray lithography, we have the high power requirement, and one of the disadvantages is it needs a synchrotron facility, right, to pattern the large area. And here we need one more disadvantage of this particular X-ray lithography is here we need the thick mask is required here. And one more is that with complex mask fabrication. The mask fabrication is also somewhat difficult in X-ray lithography while using this type of lithography, right? That is X-ray lithography. So that's why the characteristic, one of the important characteristics, feature size is around 70 to 80 nanometers. Advantage is high resolution, large area patterning, And these are some of the disadvantages where we need to implement X-ray lithography. So when we speak about E-beam lithography, the feature of the characteristic properties, here it is around 75 nanometer, energy requirement is 60 joule per centimeter square, equipment cost is around $1 million, and throughput is 10 power 4 features per second. So here the equipment cost is $1 million, which is very costly, right? $1 million. So advantages is direct patterning on the substrate. The direct patterning of substrate can be done. We can have the high resolution and high aspect ratio features. And the disadvantage is it is a slow process. Disadvantage of E-beam lithography is slow process, and the scattering of electron takes place. So slow process in the sense, if you want to write a pattern, suppose if you take this is a silicon substrate, and if you want to write a pattern like circular pattern, right? If you take circular pattern, right, whose diameter is 225 nanometers, or whose diameter is 335 nanometers, right? So generally, for using E-beam lithography, generally if you use E-beam lithography and try to write this pattern on this particular circle, right? So circle, then the patterning of this particular circle on the substrate, right, around 225 nanometer diameter, takes around 24 hours, right? So that means it's a very slow process to write on the pattern, right? So patterning on the silicon wafer using lithography is a slow process. And moreover, the scattering electron scattering also takes place more. So that is one of the disadvantages. Those are some of the disadvantages of using E-beam lithography. And we have the certain advantages. So the advantage is direct patterning of substrate. Pattern can be written directly substrate. The etching can be done, and high resolution, and also maintains high aspect ratio, right? So when we speak about the focused ion beam, so the characteristics of focused ion beam are feature size around 50 nanometers. Right, energy required is 22 joules per centimeter square. Equipment cost is $1 million here also. Throughput is 10 to the power 1 to 12 features per second. And advantages are low scattering of ion. Low scattering of ion takes place, and direct substrate fabrication. Fabrication substrate is direct here. And the disadvantage here also, focused ion beam is also a slow process. It is a slow process, and there is a change in surface properties. Right? So these are some of the disadvantages of focused ion beam. Where are the advantages of low scattering of ion, direct substrate fabrication, right? And the characteristics of feature size around 50 nanometers, energy source around 22 joules per centimeter square, equipment cost is $1 million, throughput is 10 to the power 1 to 12 features per second, right? So this is what some information regarding focused ion beam. So another important lithographic technique is deep pen lithography. This is also one of the technique where the patterning can be done on any substrate. So for example, magnetic storage devices, right? So it has its own characteristics. So those characteristics of feature size is around 10 nanometers, and equipment cost is around $0.2 million. Equipment cost is around $0.2 million. And the writing speed is around 0.2 millimeters per second. The write speed is around 0.2 millimeters per second. And the advantages is it is high resolution is possible. In this advantages, high resolution is possible here, right? Then the disadvantage is it is a slow process, right? Of course, all the lithography techniques are slow process, right? Because writing or patterning on a substrate will be a very long time process. It is a long time process. Because to write a pattern on any substrate is not a simple thing. It's not a very fast thing, right? So this will become one of the advantages for all types of lithography techniques, right? So this is what the disadvantage is slow process. So if you go for another type of lithography, that is a nanosphere lithography, here also the feature size is around 200 nanometers. The feature size of this particular nanolithography is 200 nanometers. And the equipment cost is around $5.6 million. The equipment cost is around $5.6 million. And the advantages is provide control of interparticle spacing. So provide the control of interparticle spacing. Interparticle spacing in the sense, it depends upon the Coulomb potential, right? The interparticle spacing, this is what we can write. So this is what the potential V of R and the interatomic spacing are, right? So it depends. The advantages provide control. The physics behind is what we can understand between the Coulomb potential and the intermolecular spacing. The advantage is provide control of interparticle spacing, and the disadvantage is there is a irregularity irregular geometry of MISA, right? So the characteristics feature size is around 200 nanometers, and the equipment cost is around $5.6 million, and the advantages is provides a control of interparticle spacing, right? And the disadvantage is the irregular geometry of MISA. If you go for another type of lithography, that is nano imprint lithography, the characteristics features that depends on the master, right? So the characteristic features depends on the master, right? So equipment cost is around $1.1 million, and the throughput is around 10.12 features per second. And the advantages are it's high throughput. The advantages of it is a high throughput around 10.12 features per second, right? It's low cost and insensitive to substrate waveness, right? Insensitive to substrate waveness. So these are the different advantages of using this type of imprint lithography, that is nano imprint lithography. And other is projection lithography. When we speak about projection lithography, we have certain characteristics, like characteristics like E-beam, right? E-beam, where the feature size is around 50 nanometers and the equipment cost will be around $10 million, and focused ion beam size is around 75 nanometers and equipment cost is $10 million, and throughput is around 10 features per second. And the advantages of using this projection lithography is large scale patterning is required. Here, the advantages is we require the large scale patterning used for transistor manufacturing also. This is also used for transistor manufacturing also. One of the disadvantages of using this projection lithography is E-beam suffers from scattering. E-beam suffers from scattering. This is one of the disadvantages for using this type of lithography, that is projection lithography, right? So these are the certain properties where we need to understand about the projection lithography. We have in this we have the illuminator and laser source is allowed to fall on this particular illuminator and then placed on a photomask and projecting lens where we can get the wafers, right? So where we can get wafers, right? So this is what regarding the projection lithography. So we have one more important technique for the patterning of magnetic storage devices is feature size. Is nothing but the feature size of micro contact printing technique, whose feature size is around 100 nanometers. The advantage, whose feature size is 100 nanometers, and if you see the advantage here, high throughput is possible. High throughput is possible, right? Earlier the throughput is around 10.12 per second, right? Here high throughput more than 10.12 may be possible, right, for using this type of technique that is called micro contact printing technique. So high throughput is possible and cost is relatively low. The cost is relatively low once an appropriate master has been fabricated. The cost is relatively low once an appropriate cost has been fabricated. One of the disadvantages of using this particular technique is master can take many hours even. The master can take even many hours, right? So one of the important disadvantage for using this particular micro contact printing technique is the patterning of any topological parameter on a substrate. The patterning or writing part may take so many hours, even it may take some days also, right? So that's being one of the disadvantage of using micro contact printing technique. Rather, the advantage is there. The advantage is there is a high throughput is possible here. There is a high throughput is possible, right? When compared to nano imprint lithography, where nano imprint lithography has 10.12 features per second. So here the high throughput, whereas in case of micro contact printing technique, the feature we can expect high throughput possible, more than 10.12 features per second, more than 10.12 features per second can be also be established using this type of micro contact printing technique, right? So if you see the self-assembly, right? So self-assembly like using block core polymer lithography. So self-assembly like a block core polymer lithography, phase separation of copolymer into pattern, and feature size of 25 nanometers. Right? Feature size of 25 nanometers. Phase separation of copolymer into pattern, that is feature size of 25 nanometers. So in this technique also we have certain disadvantages. So those disadvantages, ordering only in area of micrometer range, right? Only in area of micrometer range is possible. So it is difficult to scale up. It is very difficult to scale up certain phenomena. That is what a block copolymer lithography, phase separation of copolymer into pattern, feature size of around 25 nanometers. One of the disadvantages is ordering only in area of micrometer range possible, difficult to scale up. So see here, if you can observe here, we have this particular PPS, so polymer, right? Polymer is silicon. On silicon substrate, we have certain layers, right? Certain layers, and we can observe the ion beam etching here, where you can see the patterning, right? So this type of patterning is what we call it as self-assembly. So every equipment has its own advantages and disadvantages. The question, the parameter rises, is how far you can use that, and how quickly a pattern can be written on a particular substrate, right, for the fabrication of magnetic storage devices, right. So that is a nanoparticle pattern media. In case of carbon nanotubes, so patterns of size 2 nanometer is possible, right? 2 nanometer is possible. Aligning metallic and semiconducting nanotube over large area is difficult. Production of metallic and semiconducting nanotube separately not possible. Iron platinum nanoparticle self-assembly in feature size of 4 nanometer. Suffers from aggregation of particles during processing, right? So these are the self-assembly, these are the nanoparticle pattern media, right? So in carbon nanotubes, the patterns of size 2 nanometers is possible. Aligning metallic and semiconducting nanotube over large area is difficult. So production of metallic and semiconducting nanotube separately not possible. So when we speak about iron platinum nanoparticle, the self-assembly in feature size of around 4 nanometers suffers from aggregation of particles during processing, right? So this is what we can understand using nanoparticle pattern media. So if you see a comparison, as we told, the comparison between the different types of techniques, lithographic techniques, that is what interference lithography, extremely ultraviolet lithography, X-rays lithography, E-beam, and focus ion beam, and the process of taking that particular techniques, right? So the comparison, whereas in interference, the equipment cost in $1 million is around $1 million, whereas the feature size is 75 nanometers. And the throughput of features is 10 power 10, and energy joules per centimeter square is given as 4. Joule per centimeter square is given 4, right? There are no comments here. And here we see about the extreme ultraviolet lithography. The equipment cost is around $10 million, right? And the feature size is very less, around 35 nanometers. And the throughput is 10 power 11 compared to throughput is more compared to 10 power 10, 10 power 11. The throughput features of interference lithography and extreme lithography. The extreme lithography we have 10 power 11, which is where the throughput features per second is more compared to interference lithography. And the energy that is also consumed, energy joules per centimeter is 40. And there are no certain comments here. And we use the X-ray lithography. We have the feature size around 80 nanometers. And here the additional property of synchrotron is required. In case of X-ray lithography, where the feature size is around 80 nanometers. When we use E-beam lithography, the cost equipment is around $3 million, and the feature size is around 75 nanometers. And the throughput features per second is around 10 power 4 seconds. 10 power 4 features per second. The throughput is very less here compared to interference and compared to extreme lithography and interference lithography. So, is the energy joules per consumed energy joules per centimeter square. Whereas in case of focus ion beam, we have the $3 million cost equipment, and the feature size is around 50 nanometers, and the throughput features around 10 power 1 to 2. It's not more than that. So out of all these, you can go for 10 power 11 extremely high lithography. When we see about lithography when we see the lithography in throughput features per second, we can go for this particular feature. And the energy is 22 joules per centimeter square. So this is what a small comparison of lithographic techniques, what we have seen in our previous slides, right? So when we go for the projection form, so the EB projection, the cost equipment is around $10 million, and feature size around 15 nanometers, and throughput features 10 power 12, and energy consumed is 15, and the comments are large scale process, right? So energy consumed is 15 joules per centimeter square, and whereas in case of focused ion beam projection, we have $3 million, okay, and feature size is 75 nanometers, and throughput features is around the 10 power 10 features per second, right? Energy joule per centimeter square is 15. It is a large scale process. So deep pen lithography is around 0.2, and we have feature size of 10 nanometers and throughput features at 10 power 4, and there are no significant comments. Whereas in case of nano imprint lithography, we have the equipment cost is $0.1 million and depends upon the master of writing it, right? And there are no significant features, and the throughput may be more, right? May be more compared to other type of lithographic techniques. So when we speak about deep pin lithography to produce master, the cost of equipment is around $2 million, right? And the tip speed is around 0.2 millimeters per second. The tip speed in the sense when we take this as a substrate, right? This is our substrate, and we write the pattern. This is what the writing pattern. Nano patterned ink. This is right. Nano patterned ink, and it starts writing from here, and it starts writing from here. Start writing from. So this is what the writing direction. Start writing from here. Okay, so that means the direction of writing will be taking like this. Okay. So this is what the general process that takes place, right? So in deep pin lithography, right? The substrate. The same way when we pattern, on a magnetic pattern on silicon substrate, the patterning can be like this or spin up, spin down. When we speak about magnetic storage devices, right? The situation will differ. The size of the pattern here is around 14 to 20 nanometers, and the spacing is around 20 nanometers, and time to pattern is around 6 days. 1 centimeter square equals to 6 days using 10 tip. But 10 tip in the sense there will be cantilever connecting with the tip, and tip will firmly poke on that particular substrate to write that pattern. So that is what the importance of using deep pen lithography. So when we speak about nano imprint lithography for replication, we have using the SEM image. This is for SEM image whose dimension is calculated 1 micrometer here, 1 micrometer, and this is the SEM for using photopolymers, right? So these are all the AFM and MFM images. MFM images of particular lithographies that have been used for replication. So this is what make master by E-beam lithography, that silicon dioxide, form stamp by photopolymerization, and form replica by photopolymerization, transfer pattern by reactive ion, etching, and evaporate magnetic film. This is what nano imprint lithography for replication. And the results of nano imprint lithography are area coating of 3 centimeter diameter is possible. Error 5 or 3000 defective MESA. Dimension of MESA is around diameter 30 nanometers and height is 30 nanometers. Spacing around 80 nanometers, and bit density is 15 gigabytes per centimeter square. So the cost analysis is the cost of production, assuming that cost of production almost similar to transistor manufacture, and chip cost by optical lithography is $145 per chip, and one chip is around 2160 to 10 power 6 transistors. The production is approximately 24,000 chip per year, and the cost of optical lithography will be around $1.8 million. The cost of imprint lithography is $0.1 million, and chip cost by imprint lithography is $74.2 per chip. So area of the chip diameter around 3 centimeters, around 7 centimeters square, and bit density is 16 gigabyte per centimeter square, and the cost per bit is assumed to be 0.66 per gigabyte. So the summary is proposed process has potential to make inexpensive data storages, right? Proposed process is extension to current setup. So this is what the summary we can. That means everything will depending upon the cost production, and how to process the potential about a proposed process, right? To has potential. This proposed process has potential to make inexpensive data storage. Right? So in extension to current setup and the current data storages. So these are what the references have been taken. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.